We ended the video where we introduced relations by defining a subset of the Cartesian product A cross B as being a relation from A to B. And the example that we gave was where we picked an element from A, we picked an element from B, had the ordered pair AB, and it was in the relation if A divided B. So here we had 1 divides 4, 1 divides 3, 1 divides 2, and so on. So I would say 1 is related to 4 under this relationship of divisibility. Now, mathematics is all about generalizations and finding patterns and using an established set of properties to say, well, if a particular idea has these properties, then I know it has these properties, and some other properties. So in the context of relations, what properties, how might I classify relations? If I start with the set A, I would say that a relation is reflexive if I work out the Cartesian product A cross A. I'd say the relation is reflexive if all elements from A are related to themselves. So A are A, for every element I pick from the set A, that element is related to itself. I can also say that a relation is symmetric if I pick any two elements from the set. Then if A is related to B, that implies that B is related to A. If for all pairs that I could pick A and B, I have this implication. I also have, as well as symmetry, I have the concept of anti-symmetry, and that's if for all elements I pick from the set, pick a little a and a little b, the only way that A is related to B and B is related to A is if I pick the same element twice, if A equals B. And I also have this transitive property, which says if I pick 3 elements, A, B, and C, if A is related to B and B is related to C, that must mean that A is related to C. So I can kind of pull that relation through. So those are the 4 main characteristics by which I might classify a relation. Now that we have the definitions of the 4 properties or characteristics of a relation defined, we'll do a practical example with this. Our 4 definitions were if a relation was reflexive, symmetric, antisymmetric, or transitive. And a relation may be any of those, or all of those, or none of those. So I'll start with a set A containing 3 elements, x, y, and z, and the relation being the subset of A cross A, containing the ordered pairs xx, xy, xz, yy, yx, and zx. And I'm going to ask whether this relation should be characterized as reflexive, symmetric, antisymmetric, or transitive, or any number of those. Okay, my definition of reflexive says that every element has to be related to itself. So if I pick x, well, xx is in the set, so x is related to itself. If I pick y, I have yy in the set, so y is related to itself. If I pick z, zz is not in the set, so z is not related to itself, and because z is not related to itself, that means that the relation is not reflexive. How about symmetry? Well, every time I pick two different elements, x, y, I've also got yx in there. If I pick xz, I've also got zx in there. So because every ordered pair also appears with the order reversed, then it's symmetric, and trivially xx and yy don't break the symmetry. What about anti-symmetry? Well, no, because I've got xy in there, and I've got yx in there. But xy and yx both being in there, where x is not the same as y, tells us that it's not anti-symmetric. And transitivity, I can check by showing that I have yx in there and xz in there, and if it were transitive, y being related to x and x being related to z would tell me that y is related to z, hence yz is in the set, which it isn't. So the only one of these four categories that I can describe the relation as is symmetric. Let's do another example. If I start with A being the set of all positive integers, I'll define the relationship R to be all ordered pairs xy, such that x is from this set A, from the set of positive integers, and the second element of the pair y is also a positive integer, and x divides y. So there'll be an infinite number of elements in this relation. But I'll ask the same questions. Is it reflexive? Is it symmetric? Is it anti-symmetric? Is it transitive? Well, reflexive, I only have to be convinced that every element is related to itself, and I think I'm reasonably convinced that every positive integer divides itself. And so, yep, 7 divides 7, 10 divides 10, 38 divides 38. Every positive integer is divisible by itself. Is it true that if x divides y, that y has to divide x? No, it's not, because 5 divides into 10, 10 doesn't divide into 5. So this is not symmetric. Is it anti-symmetric? Well, yes, because if I know that something is both a divisor and a multiple of another number, it has to be the same number. I can say that 10 is a multiple of 5, but 5 isn't a multiple of 10. But I can say that 10 divides 10 and 10 is a multiple of 10. I can say that 17 divides 17 and 17 is a multiple of 17. So the only integers which are both divisors and multiples of a given number is the case when the first integer I'm interested in is the same as the second. What about transitivity? Well, yes, because if I've got that A divides B and B divides C, then A has to divide C.